Welcome to an in-depth exploration of emulsions, double emulsions, and core shell droplets in microfluidics. Imagine tiny liquid droplets suspended in another liquid, like oil droplets in water or water droplets in oil. These are emulsions, the foundation of microfluidics. Let's start by understanding what emulsions are and how they form in microfluidic devices. An emulsion is fundamentally a mixture of two liquids that don't normally mix, like oil and water. One liquid forms tiny droplets that are dispersed throughout the continuous phase of the other liquid. Here's a water and oil emulsion, where water droplets are dispersed in the continuous oil phase. This is one of the two basic types. And here's an oil and water emulsion where oil droplets float in a continuous water phase. These are the two fundamental emulsion types. Interfacial tension is the critical force that governs emulsion formation and stability. Interfacial tension, denoted gamma, is measured in millinewtons per meter and represents the energy at the liquid-liquid interface. At the interface between water and oil, molecules experience unbalanced forces, creating interfacial tension that tries to minimize the contact area. Typical interfacial tension values between water and oil range from 20 to 50 millinewtons per meter. The Young-Laplace equation describes the pressure difference across curved interfaces, fundamental to droplet formation. The Young-Laplace equation states that pressure difference equals interfacial tension times the sum of inverse principal radii of curvature. For a spherical droplet, both principal radii are equal to the droplet radius r. This simplifies to delta P equals 2 gamma over r for spherical droplets. Pressure inside a spherical droplet is higher than outside, with the difference proportional to interfacial tension and inversely proportional to radius. Let's calculate the pressure difference for a droplet with radius 50 micrometers. Using an interfacial tension of 30 millinewtons per meter and radius of 50 micrometers, the pressure difference equals 2 times 0.03 divided by 50 times 10 to the minus 6, giving 1200 pascals. Microfluidic devices generate droplets with precise control using channel geometries and flow rates. In a T-junction microfluidic device, the dispersed phase enters from above while the continuous phase flows horizontally, creating uniform droplets. Flow-focusing geometries create highly uniform, monodispersed droplets with controlled sizes. Droplet diameter is proportional to the ratio of dispersed to continuous flow rates times the channel width. Consider a dispersed flow rate of 10 microliters per hour and continuous flow rate of 100 microliters per hour. The flow ratio is 0.1 with channel width 100 micrometers. This produces droplets approximately 10 micrometers in diameter. Double emulsions are like Russian nesting dolls made of liquids, with droplets inside droplets. A water in oil in water double emulsion has water droplets inside an oil shell, all suspended in water. Like Russian nesting dolls, the structure consists of inner droplets of one phase encapsulated within an outer droplet of a different phase. WOW notation means water droplets inside oil, inside water continuous phase. OWO notation means oil droplets inside water inside oil continuous phase. An oil in water in oil double emulsion shows oil droplets inside a water shell within oil continuous phase. The spreading coefficient determines whether double emulsions are stable or will collapse. What interfacial tension conditions are required to stabilize a double emulsion? Let's derive the answer. The spreading coefficient S equals gamma oil water minus the sum of gamma water middle oil plus gamma middle oil water. For a stable water in water emulsion, the spreading coefficient must be negative. S less than 0 implies that gamma oil water must be less than the sum of the other two interfacial tensions. The three interfaces in a double emulsion each have their own interfacial tension that must be balanced for stability. Let's calculate a spreading coefficient with realistic values. Outer oil-water interfacial tension is 25 millinewtons per meter. Water-middle oil tension is 15, and middle oil-water tension is 12 millinewtons per meter. The spreading coefficient equals 25 minus 27, giving negative 2 millinewtons per meter. Since S is negative, this double emulsion configuration is thermodynamically stable. Creating double emulsions requires sophisticated microfluidic designs with multiple junctions. A two-step microfluidic device first creates water in oil droplets, then encapsulates them in water at a second junction. Step 1 forms water in oil droplets at the first T junction using oil as continuous phase. Step 2 encapsulates these water in oil droplets within water at the second junction. By adjusting flow rates independently at each junction, we control both core and shell dimensions. Core shell droplets have precise geometric relationships between inner and outer dimensions. A core shell droplet has core radius RC, shell inner radius RS, and total outer radius R. Shell thickness T equals outer radius R minus shell inner radius RS. Let's design a 100 micrometer diameter core shell droplet. Total radius is 50 micrometers, with core radius 15 micrometers. Shell inner radius is 20 micrometers, giving shell thickness of 30 micrometers. Shell volume equals 4/3 pi times r cubed minus rs cubed. This gives approximately 490,000 cubic micrometers of shell volume. Advanced designs can encapsulate multiple cores within a single outer shell. Multiple small cores can be distributed within a single oil shell, creating multi-core capsules. The number of cores is controlled by the ratio of inner to middle phase flow rates. Number of cores is proportional to the flow ratio times the oscillation frequency of breakup. Pressure differences across multiple interfaces must balance for stable double emulsions. What interfacial tension conditions are required to stabilize a double emulsion? Let's examine the pressure balance. Pressure jump at inner interface equals 2 gamma 1 over inner radius. Pressure jump at outer interface equals 2 gamma 2 over outer radius. Core pressure PC must balance against both pressure jumps through the middle and outer shells. Core pressure equals outer pressure plus both pressure jumps. Let's calculate actual pressure values for a specific droplet. Inner radius is 10 micrometers and outer radius is 40 micrometers. Inner interfacial tension is 15 and outer is 25 millinewtons per meter. Inner pressure jump equals 3,000 pascals. Outer pressure jump equals 1,250 pascals. Total pressure difference from core to outside is 4,250 pascals. Double emulsions enable encapsulation of living cells for biological studies and therapies. Living cells are encapsulated in water droplets, protected by an oil shell, suspended in aqueous medium for long-term culture. Cells remain viable inside the aqueous core, which provides nutrients and maintains proper osmotic balance. The oil shell acts as a protective barrier against harsh external conditions while allowing small molecule diffusion. Each encapsulated droplet functions as an independent microbioreactor for single-cell studies. Food industry uses double emulsions to encapsulate and protect flavors and aromas. Oil-based flavors are encapsulated in oil droplets within water shells, protecting them from oxidation and degradation. The oil in water in oil structure protects volatile flavor compounds from environmental degradation. Controlled release occurs during consumption when mechanical or enzymatic forces break the shells. Double emulsions keep reactive components separated until triggered mixing is desired. Reactive components A and B are kept in separate cores within the same shell, preventing premature reaction. The reactive components only mix when the protective oil shell is deliberately broken. This principle is used in self-healing materials where damage triggers mixing and polymerization. Precise control of droplet size is achieved by manipulating flow rates and channel geometry. Droplet diameter equals a constant times flow ratio to the power beta times channel width. The constants alpha and beta depend on the specific microfluidic device geometry. Typical values are alpha between 1 and 2, beta between 0.3 and 0.5. Increasing the flow rate ratio produces larger droplets, as shown in these three size distributions. Let's calculate how to scale droplet size from 20 to 100 micrometers. The size ratio equals the flow ratio raised to power beta. We want a 5-fold size increase with beta equals 0.4. The flow ratio must increase by 41-fold to achieve this size change. Independent control of shell thickness is critical for optimizing encapsulation properties. Shell thickness equals outer minus inner radius, proportional to middle phase flow rate. Increasing the middle phase flow rate produces thicker shells at constant core size. Same core size with different middle flow rates produces thin versus thick shells. Let's design shell thicknesses ranging from 5 to 20 micrometers. Fixed outer radius of 50 micrometers and core radius of 20 micrometers. For 5 micrometer shell, inner shell radius is 45 micrometers. For 20 micrometer shell, inner shell radius is 30 micrometers. Surfactants are essential for stabilizing emulsions by reducing interfacial tension. Surfactant molecules align at the oil-water interface with hydrophilic heads in water and hydrophobic tails in oil. Surfactants dramatically lower interfacial tension, making droplet formation easier. With surfactants, interfacial tension drops to 1 to 10 millinewtons per meter. Without surfactants, tension is 20 to 50 millinewtons per meter. Double emulsions require different surfactants for each interface to maintain stability. Understanding coalescence mechanisms is crucial for long-term emulsion stability. Droplets can approach, touch, and merge through coalescence when interfacial films break down. Coalescence time depends on how fast the thin film between droplets drains away. Coalescence time is proportional to viscosity times radius divided by interfacial tension. High continuous phase viscosity and low interfacial tension help prevent droplet coalescence. Triple emulsions add another layer of complexity with 3 nested liquid phases. A water and oil triple emulsion adds another water and oil core inside the oil shell, further expanding encapsulation capabilities. The number of layers in nested emulsions is limited only by the sophistication of microfluidic fabrication techniques. Each additional layer requires careful selection of surfactants and balancing of interfacial tensions to maintain stability.